so far we have used two beams and they are coupling. In non-collinear configuration, one can also use three beams. So I have a medium, I have this three beams propagating like this way, they are interacting in the medium, and if we have three beams, then an additional beam will be created. And if the additional beam is created, I'll change the color, let's say again I'll create a blue, and I'll say that okay, I have created an additional beam along this way. So effectively what we do here is that in nonlinear process we have three input beams interacting and giving another output beam. Total 4 beams are in the interaction region, and that's why we call this kind of processes as 4-wave mixing. There are 4 different waves which are getting mixed together. That's why 4-wave mixing. Similarly, if we go back to our previous work, previous slide, we have discussed 2-beam coupling, and 2-beam has created a new beam. So I have total 3 beams which are getting coupled. So this is my third beam. So there are 3 beams which are getting coupled. Here 4 beams are getting coupled, and so here 3 beams are getting coupled. We can call this process as 3-wave mixing. So this is the way. There is another way of naming these processes. So we will go back to this 4-wave mixing. In 4-wave mixing, we have 3 beams coupled and 1 more beam is created. That's why it's 4-wave mixing. The real resultant field due to 3 input beams can now be represented by, so I have a medium, I'll change the color. I have a medium, and then there are 3 beams which are getting coupled in the interaction regime in the medium at this point. So if I have 3 beams, E1, E2 and E3, then we know that fields would be additive. At this point, electric field, real field is going to be nothing but this. The first beam, complex notation and its conjugate, complex notation going to the second beam, and the third beam. So if I consider third order response, then I have this cube term, and finally this whole equation is reduced down to the simplified 10 standard equation, which is a plus b plus c plus d plus e plus f cube, which will have many terms. Among them, we'll select only very important 2 terms. One is ADE, another one is ADF. For ADE, if we look at ADE term, then I can write down this term can be written down as A is A1T. From here it is A, this is B, this is C, this is D, this is E, and this is F. So ADE term is going to be A1T e to the power I omega 1T minus K minus K1Z multiplied by D, which is A2 star T e to the power minus I omega 2T minus K2Z multiplied by E, which is A3T e to the power I omega 3T minus K3Z. So this is my ADE term, which can be reduced to this can be reduced to this equation A1 A2 star A3 e to the power I omega 1 minus omega 2 plus omega 3 T minus K1 minus K2 plus K3Z. this can be simplified. A very interesting variant of this term is obtained when we take identical 3 input beams. Let's say these 3 input beams are coming from the same the same input beam. So we can split an input beam and we can use identical 3 beams. If they are identical, then what we get, this equation will be reduced down to this equation, A1T modulus square, then A1T e to the power I omega 1T minus K1Z. If we use identical 3 beams. What does it mean? It means that I have this beam, which is the input beam E1, they are identical, so all are E1 now, all are E1, E1 and E1. Their propagation directions are different, but their propagation directions are different, but they are still E1 beam. So that can be expressed by this. So this beam, what we are seeing is that if we have identical 3 beams due to this third order nonlinear process associated with this ADE term, we can get back a beam, new polarization is created, which is again getting affected by its own intensity. A1 square modulus is nothing but its own intensity. So intensity of the beam affects itself. We have already seen that 2 such important self-affecting processes, self-phase modulation and self-focusing. These are the 2 self-affecting processes we have already seen. But instead of taking all identical beams, we can also consider 2 identical beams and a second beam. So instead of taking, when we take 3 identical beams, we call degenerate 4-wave mixing, and there are 2 consequences of degenerate 4-wave mixing. One consequence is self-phase modulation, another one is self-focusing. But if we do not consider 3 identical beams, instead of 3 identical beams, we can consider 2 identical beams interfering like this way. These are 2 identical beams, and this one is the third beam, is a different beam. So let's say this is E1, this is E1, and I call this one is E3. One can say E2 also, doesn't matter the way we are representing by ADE term, that's why we are calling it E3. It's just a matter of convention. So now if we use E3 term, then what will happen? Due to this nonlinear process where 2 beams are identical and 1 beam is different, then what will happen? Part of this E3 beam will be diffracted back along this way, and we create diffracted back along this way, and this is called transient grating, and this diffraction occurs due to the transient grating. So what happens? I will show the maths which is responsible for this phenomenon, but I'll give you the idea immediately. Coupling of these 2 identical beam creates transient grating in the medium. In the medium, if we magnify this region, we'll see that in the medium transiently we create a grating like this. And due to this grating, now I have E3 is coming, and this E3 is getting Bragg diffracted like this way. Part of this beam will be Bragg diffracted. So this diffraction occurs due to the transient grating created by the 2 identical laser beams. So this ADE term, we have to look at this ADE term, and the transient grating which is responsible for this is going to be E1 star E3. So this is your E1, this is E1 star, and this is E2, this is E2 star, and this is E3, and this is E3 star. So basically we are saying that E1, these 2 are identical, so they are identical, so we have made it 1. E2, there is no E2 here, and so it is still in ADE terms. This is A, then B, C, this is D, and then this is this is E term. So this is ADE term, and we are seeing that ADE term here is E1, then E1 star, yes, E1 star this one, and then E3, this E3 term. So the transient grating will be created when two identical pulses are interacting with another third beam. So these two identical beams, E1 identical beams, will create the transient grating, and the third beam will be Bragg diffracted due to this grating. So let's understand what does it mean by this transient grating and how we create that. Let us consider that K1 and K2, these are the K1 and K2 are wave vectors of the excitation pair pulse, the pump pulse, let's say. These are the identical pulses we are talking about. So we are now looking at the E1 is star 1 term first. So in order to look at this, they are interacting at an angle 2 theta angle. So basically with the z axis they are forming theta angle, and they are interacting like this way. If these wave vectors are decomposed into the components along the z direction, this is the positive z direction and this is the positive x direction. We are going to decompose these two wave vectors along these two directions. Then one can write down that K1, this wave vector, equals K1 magnitude cos theta, this K vector, it is a unit vector along the z direction, plus K1 magnitude sin theta I is again unit vector along the x axis. So I is unit vector along x axis and K cap is the unit vector along the z axis. So I can decompose this K1 along the z and x axis. On the other hand, K2, similarly we can write down this K2 vector can be written down as K2 magnitude of cos theta along z direction minus is because I am now decomposing along this direction. So this is minus x direction. On the other hand, for K1 we have decomposed along this and this direction. That's why this minus sign, we are getting minus sign for the K2. We can write down this minus K2 magnitude sin theta I. So this is an expression which we get immediately if we decompose these two vectors K1 and K2 along that z and x axis. Once we have decomposed it, then as these two excitation pair pulses are taken to be identical, we can write down that this K1 magnitude, their directions can be different, but the magnitudes are the same because they are identical. We have said that we are looking at identical two beams, and that can be written as K, which is nothing but 2 pi n by lambda. N is the refractive index of the medium. This expression is already obvious to us because in mathematical formulation or representation of ultrafast pulses, we have seen that how the magnitude of the wave vector is related to the wavelength. And so two pulses interfering at an angle 2 theta exhibits the same magnitude of k vectors, but their propagation directions are different. So we have to remember that although the propagation, this K1 and K2 we are representing because their directions are different, but their magnitudes, the wave vector magnitudes are the same. So if we have this to a relationship, then we can take a look at the first two terms. We are going to look at this E1 star. We are actually interested in, finally we are interested in E1 star E3. This is the term we are interested in, but first we will look at this first two term and what is the effect of this, consequences of these two product. So we will write down these consequences. A1, it is nothing but A1t e to the power I omega 1t minus K1 dot R multiplied by A1 star t e to the power minus I omega 1 t minus k2 dot r. We are saying that E1 multiplied by E1 star, but this is actually E2 star, which is equivalent. E1 and E2 are the same thing. So these two terms, we have to get the product of it, and if we get the product of it, so basically here E1 star or E2 star, they are equivalent. Okay, so we should remember this one. Although we are presenting as E1, but that's why it is actually, it can be, that's why we are taking this K2. That's the two directions are different. So this is E1, this is E2, but we are representing, their only difference is the K2, that is the direction. So now if we simplify this one, we get A1 square modulus multiplied by e to the power I. This omega 1 is cancelling out, so I get only minus K1 plus K2 dot r. This omega 1 will cancel out because there is a negative sign here and there is a positive sign here, so they will cancel out. So if I further now plug that in the previous expression, we have decomposed K1 and K2 vectors along the x and y direction. So that decomposed expression, if we write down here, is going to be square e to the power I. Now I can write down this one as minus k, that is the magnitude, cos theta, then direction, this is the unit vector along the z direction, minus k sine theta, then I, that is the unit vector along the x axis, plus k cos theta, then k is the unit vector along the z axis, minus k sine theta I, unit vector along the x axis, dot r. This is what we get. We can further simplify by A1 square modulus square e to the power I, then minus 2 k sine theta I dot r. This is what we get, because this cos theta is cancelling out, so I get only sine theta term. And r can be now decomposed into its characteristic x, y, z directions. So I can write down e to the power I minus 2k sine theta, then I dot r can be written as I x plus j y plus k z. This is the way we can write down, and we know that I dot I will exist, other will cancel out, it will become 0. That's why we can write down as e to the power minus 2 I k x sine theta. So this is the term which we get finally as a result of the product of these two identical beams. And taking only the real part of this, what we get is that this real part of this E1 star, that we get as A1 t square modulus, then real part is going to be cos of that function, so 2 k x sine theta, cos of that function. And k, we know that it's going to be, previously we have already written that cos, k is going to be cos, then 4 pi n by lambda x sine theta. This is 2 pi for k, and this multiplied by 2, that's why we get 4 pi. So this is the expression what we get for the real field. And what does it mean? It means that the joint effect of first two identical pulses or beams results in sinusoidal variation of intensity in the sample, which causes spatially varying population of ground and excited state species along the transverse direction as shown here. So what does it mean? It means that this real field is showing variation of the intensity. So this is variation of the intensity along the x-axis. What is x-axis? It is the transverse direction along this direction. So if the medium is like this, and if two beams are interacting along this direction, they are propagating along this direction, this is my z direction, then what I am getting is that variation of the intensity will occur along this direction, along the z direction. Along this z direction, I will have a variation. And what does it mean by variation along this x direction? Sorry, this is x direction. Variation of intensity along the x direction, it means that, let's say this is intensity. So this intensity will be modulated by x direction, x axis. Okay. Now cos value for a certain x, I'll get cos value 0, which means intensity will be 0. Or for a certain value of x, I'll get cos value maximum, which will get maximum intensity, which means that along this x-axis direction, I'll have intensity of this beam to be going up and down with respect to 0. So this is your 0 value. With respect to 0 value is going up and down. And when a medium, I have also, what does it mean? It means that along this x-axis, because this is the regimes where we are getting intensity, right? And there are regimes where we don't get intensity. The intensity becomes 0, which is shown here with the help of this this color, this green color. So in this green color, positions are 0 intensity. So we are getting 0 intensity here. So what will happen? Because in order to excite a molecule, few molecules, let's say I have in this medium, I have different molecules in this medium, and what we see along this x-axis, we see a spatial variation of the excited state species and ground state species. This green color positions will have no intensity. It means that molecules will not be excited to the excited state. On the other hand, these red color positions having high intensity, which means maximum number of molecules will be excited to the excited state. So effectively, this variation of the intensity along the x-axis will create a variation of the excited state population in the medium. And that excited state population is creating a different refractive index. So what does it mean? It means that the medium refractive index here and medium refractive index here are different. So I have a medium now where I have transiently created this grating, and these points having different refractive index compared to this empty space. And if you have a variation of the refractive index, that means if I have a third beam coming along this direction, it will be diffracted back due to this grating, and that's exactly what we have shown. The wavelength of those variation can be calculated with the help of this eta. This eta is representing the spacing between the spatial variation of the refractive indices or spatial variation of the intensity along the x-axis, which definitely depends on this lambda, the excitation wavelength. So So what we are seeing here is that the magnitude of the wave vector for the resultant field, if I have now the third beam coming, then the magnitude of the resultant field, the grating wave originated by, so basically this E1 star, this identical beams is creating a creating this spatial variation of the refractive index, and also spatial variation of the excited state species and the ground state species, or the intensity, and its wave vector can be represented by this equation. And any wave can be represented by 2 pi by eta. The eta is the wavelength of that repetition. So if this oscillation is represented by this eta wavelength, that is connected to the excitation wavelength following this equation. So this wave vector we get from the previous calculation. The calculation shows that final expression for this field is going to be depending on minus I2k x sine theta, right? So from here we can say that the wave vector is going to be this one, 2k sine theta. This is going to be the wave vector, and that's exactly what we have written here, wave vector. But for that wave vector, I have wavelength to be eta. Eta is the variation of the intensity. So eta can be written as lambda by 2n sine theta. This is the spacing of the periodic variation of the spatially varying field, and that's exactly the spacing between the excited state species and the ground state species, or the grating spacing in the transient grating created by the interaction of two identical beams. Finally, the third order polarization due to this E1 star and E3 term can be given by this A1t magnitude square A3t now e to the power I omega 3t minus 2kx sine theta I plus k3 dot r. This is the way the total polarization would behave, and this polarization kp, that polarization wave vector, can be then written as 2kx sine theta I plus k3. So along this direction we have this this new beam created. And what is that direction? I plus k3. I is along this direction, which is the unit vector along the x direction. So x plus k3. K3 direction is going to be along, so k3 direction is going to be along this direction. So this is the k3 direction, new beam direction. This is the I direction. So finally I get the beam to be like this. So this I plus k3 direction is shown here. This indicates that the emitted beam generated due to E1 star E3 third order nonlinearity features frequency same as of the third beam, but it exhibits different direction. The direction is going to be I plus k3 direction. This is nothing but the Bragg diffraction of the third beam. That's the way we get the diffraction of the third beam. Part of the beam will be diffracted back to along this I plus k3 direction. And the diffraction is created by the interaction of these two identical beams. Now, a spatial pattern of excited and ground state molecules will be created. As I've told you, that if I have along this x-axis, if I have this intensity maximum here, 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 and then intensity 0 at these positions here, then here, then here, then here, these are the positions where intensities are 0. which means that I will have a spatially varying excited state species and ground state species. Whenever I have intensity 0, it means that molecules are not excited, so that region would be will contain only ground state species, and the region where I have intensity, the region will be excited, the molecules will be excited to the excited state. So this spatial variation of the intensity created by two identical pulses will also create spatially varying excited and ground state species in the medium, and the spacing will be controlled by the equation which we have shown already. That is going to be eta it is going to be lambda by 2n sine theta. This is the way the spacing will be controlled. Now the time delayed third beam, which is the probe beam, can then be diffracted off this grating. In other words, the excitation with the pair pulse leads to periodic spatial variation of the complex index of refraction of the medium. Some space in the sample possesses excited state molecules and some in the medium possesses ground state molecules. These spaces are periodic, which behaves like a diffraction grating. Now the third beam is diffracted off the transient grating, and in the experiment the diffracted pulse energy is monitored as a function of time delay between pump and probe. The energy of the diffracted beam depends on diffraction efficiency of the transient grating. The transient grating signal depends on any process which acts to destroy the grating pattern. For example, excited state population relaxation can destroy the grating pattern, which reduces the diffraction efficiency. Thermal or mass diffusion along the x-axis can also destroy the grating pattern. Thus, by recording diffracted beam energy as a function of time delay between pump, that is the pair pulse, and probe, one can estimate diffusion kinetics of the molecules in the solution. So when we consider diffusion kinetics, we can actually write down few equations. N is the population, which will vary along this x-axis like this way, cos 2 pi x by eta. So this is the way the population excited state species will vary. And if we take the second derivative with respect to x d2n dx2 equals, this is going to be minus n naught 2 pi by eta whole square cos 2 pi x by eta, which is nothing but 2 pi by eta whole square multiplied by n with a negative sign. Now we know that Einstein diffusion equation, that is going to be dn dt equals partial derivative diffusion constant d2n dx2, which we can write as this can be, so this is positive. Now this can be written as minus d 2 pi by eta whole square n, and we can then write down, we can integrate this equation, we can write down this way, dn by n equals minus d 2 pi by eta whole square dt. This is the way we can write down, and finally what we get if we integrate it, and then we can within the limit of n naught to n, then within this limit where 0 to t limit, we get final expression as n equals n naught e to the power minus d 2 pi by eta whole square t. So as a function of time, we see that the change in population due to diffusion, and that we can monitor with the help of diffracted energy. If we use a power meter here, and if we keep looking at the energy, how the energy is changing as a function of time delay between pair pulse, identical pulse, and the probe, then we see that it's changing the diffraction. So in order to diffract this beam, I need to have this grating sustained, and this grating can be washed off due to diffusion, and that can be plotted with respect to time following this equation. So one can find out the diffusion kinetics. We will stop here, and we will continue this module in the next lecture.